Okay. This section is about exponential logs, and those are inverses of each other. But let's just talk in general. I'll try to do as much as I can in 15 minutes, and then we'll see where we're at. All right. If you look at this one is going up 20, up 20, up 20, up 1, up 1, up 1. So the change in y is always plus 20. The change in x is plus 1. That is slope. If you graph this, this is linear, all right? And its starting amount, the y-intercept is at. So I don't have to solve for that. I actually can just look at it. So my starting amount is 100, and then my rate is 20. So this would be like, say you buy a stock at month 0, it's 100. So when you first buy it, 100 bucks. And say every month this stock is going up $20. So it's going up a constant amount. You have a starting amount. So after, say, you're like, oh, after a year. Okay, well, a year would be 12 months for input. So you're like, okay, after a year, what is this thing worth? So what is that? Is that 240 plus 100? So that stock is worth $340 after a year if this trend continues. Okay, that's linear. That's a linear problem. Now this one, if you do this slope, it's like, well, this is 100 over what? 100 over 1. This is 200 over 1. This is 400 over 1. Yeah, there isn't slope, right? If it's changing constantly, the rate of change is varying between points. That is not a line. It has to be consistent all the time to be slope. So you're like, oh, nope, this thing is not linear. Okay. So if you look, it is doubling all the time, right? It is doubling from 100 to 200, then 200 to 400, and then 800. Okay, so this is exponential, okay? And these actually are easier to write than linear. Y equals, okay? You're going to have some starting amount, and then you're going to have some type of multiplier, and then you're going to have an exponent. Okay, so here my starting amount at 0, still buying the same stock, 100 bucks, right? But it is doubling every month. So 2 to the x power, okay? So it is doubling every month. So my starting amount's 100, my multiplier is 2, it's doubling all the time, and then raised to the x power. And we call it exponential because your variable is in your exponent, okay? If you have x squared plus 3x and some other stuff, that is not exponential, that's quadratic, okay? And if it had a cubed here, it would be cubic. It's when the x is in the exponent that it's exponential, okay? So again, if you have this for 12 months, x equals 12, and again, this is where on the internet, when people say, oh, it went viral, right? It basically is like it went exponential. It's like a virus, right? And it's just going crazy, okay? So if I go on Desmos, I start out with 100 times 2 and I raise it to what, the 12th power. That would be worth $409,000, $600, right? Wouldn't that be lovely? So that is the difference, exponential. Now, if it's times 2, that's kind of easy to see. In real life, you might have something like maybe your car is depreciating. Now, they used to depreciate more, but say it's only depreciating 3% per year, okay? So you have a starting amount. So say you buy a used car for $15,000. All right, what's your multiplier? Depreciating means it's losing. So 100% would be what it's worth. You're losing 3%. You're only keeping 97%, and then again per year or whatever. Okay, so this is how you'd write it. Starting amount, your multiplier, you're losing. And so this is exponential decay. This thing is going to go, you start out here and you're going to go down and you're going to get infinite close to 0. Can't equal 0 because of, it would be impossible for this to ever, because think of it like if you take half of a 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 half, yeah, it's going to get infinite tiny, but it's never going to equal 0. Okay, so this could be like, say your kidneys filter out, I don't know, say they filter out, say 25% every 4 hours, okay? Now, it kind of depends on how you write your exponent here, but say you take 500 milligrams of Tylenol or something like that, you would have 100% of the meds, but you're losing what, 25%, so you're only keeping 75%. Now, you could either say time period, and T could be sets of 4-hour time period. So 1 would be 1 set of 4-hour time period. 2 would be 2 sets of 4 hours. So 12 hours would be 3 sets, okay? If T is your sets of 4-hour time periods. If you want it to be hours, what you'd have to do on that is you'd have to say it's the hours divided by 4. Because if it's 4 hours, you only have 1 filtering. If it's 8 hours, 8 divided by 4, you'd have 2 filterings. If it was 12, 12 divided by 4 is that. So if you do kind of like, periods of 4 hours, like how many sets of 4 hours, then it's one thing. If you want to do hours here, then you have to divide by 4. Okay, so these aren't too bad to write. If it's growing, okay, say you have a 20% growth, maybe of some stock that's just doing crazy, right? So again, say you pay $200 for that stock and it's going up by 20%, then normal is 100%, but you're growing by 20%. That'd be 120%, which is 1.20. And then again, say every year, every month, or something like that. Okay, so that would be growth. All right, so if this is bigger than 1, you are growing. And if that multiplier is less than 1, you are decaying. So growth would look like we're starting at $200, right? And then we're just going infinite. Okay, it's growing. All right, let's see, what else do I want to do? Let's graph one of these. Say I give you 2 to the x, okay? So there's just input and output. If I sub in 0, I'm at 1. If I sub in 1, I'm at 2. Now this is not linear. If I sub in, let's see, that was 1. If I sub in 2, I'm at 4. If I sub in 3, 2 times 2 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8 is way up there. Now on this side, you have to sub in negatives, okay? So if you think of your input-output chart, right? I subbed in, 0, 1, 2, 3. What if I sub in -1? Well, negative exponents mean reciprocate. So that's going to be a half. -2. Well, 2 squared is 4. So -2 is 1/4. You flip it. And 3, where did we do 3? Let's see, 2 to the 3rd power was 8. So the reciprocal of that negative exponent would be 1/8. So you can see how we can keep getting fractions and fractions, but we can never land on 0. So that is going to be an asymptote. Okay, that's exponential. Okay. Now, as far as transformation on this, say I gave you y equals 2 to the negative x plus, or let's do minus, minus 3. Okay. So if you look at this graph, you're like, okay, there's a negative on the x values, right? So a negative on the x value is going to reflect it this way, right? Because these x's that were positive are going to reflect over to here. These x's that are negative are going to reflect over here. So this guy would reflect over the y-axis. All right, and then this -3, right, is going to shift it down 3. So shift down 3. So we can do transformations on these guys too. All right. Let's talk about logs for a little bit. Okay. Logs are the inverses. Okay. So remember how I talked about functions always have jobs. Okay. So if you have 2 to the 3rd equals 8. Okay. We're going to call this the base because that's what it's called. We're going to call this the exponent because that's what it's called. And for lack of a better word, we're going to call this the answer. Okay, that's just the answer. So we spit out an answer. Okay, logs are the inverses, okay, of an exponential thing. So logs eat answers. That's their job. They eat the answer, and their goal is to spit out the exponent, which in this case is 3, and the base comes here. Okay, now if you have a calculator where you can type in other bases, okay, besides base 10 or base e, you can. Otherwise, a change of base formula is important. So log of 8, log of the big over log of the base, log of the little, that should give you 3 because 2 cubed is 8. So if I just go, I don't know, I'll grab a TI here. If I go on my TI, all right, and I just clear my calculator. If I go log of 8 divided by log of 2, enter, it gives me the 3. And you can do ln too, natural log, log of 8 natural log, and stick with the same log. You can't switch gears. That also gives you 3. Okay. All right. So why is this important? Well, because in algebra, remember, what are the only 2 equations we really know how to solve? Linear and quadratic. That's it. Everything else we have to do inverses and isolate until it looks like it's linear or it looks like it's a quadratic. So say I give you something like 2 to the x equals 7. All right. Well, if we didn't have logs, what you're going to do is you are going to get on your calculator, or, you know, if you had one, or look in a chart in the old days, and you would say, 2 to the 3rd power is 8, too big. 2 to the 2nd power is 4, too small. I have to guess. I don't like guessing. 2 to the 2.5. Let's see, I want 7. No. 2 to the 2.66. No. 2 exponent 2.77. No. 2 raised to the 2.88. Too high. 2. Do you see where this is going? Not fun. Okay. So instead, logs get it on the level so it becomes linear. All right. So let's look. What do logs do? So an exponent function, exponential function, right, is going to spit out 7. Logs, their job is to eat the answer and to spit out the exponent. That's why we love them, because we want the exponent. And then the base just comes down here. All right, so the log is going to eat the answer, 7. It's going to spit out the exponent, which is x, and the 2 comes down here. Do you see how this is linear now? Like this is all on a row. Now, if you have a calculator and you know where to find other bases where you can type in the log, it might be under math or on a TI. I don't know for sure, but I always just do the change of base formula. All right, so I would just do, log of 7, log of the big, divided by log of the base, because that's a really good formula to know. See how I didn't have to guess and test? 2.807, and that's lovely. And that's an approximation, obviously. I think if you go to math, maybe, or there might be logs under there. Maybe, I don't know. It's not looking good. I don't know. You can find it, or just Google where it's at. It's somewhere, but again, I just never use it because I just do the change of base formula. All right, so I think that is pretty handy. So let's see. As far as graphing them goes, I never graph logs. I actually graph the reciprocal. So if I want to find the inverse function of here, remember any inverse function, the x becomes the input, or the x and input and output, sorry, flip-flop. So if this is my output, I'm going to call that my input. And if this is my input, I'm going to call it my output. Now, if you're like, Julie, how do I solve this? It's not linear or exponential or quadratic. I guess it is kind of exponential, but you do the inverse, and the inverse is a log. Exponential, the inverse is a log. So logs eat answers. What's the answer? X. Spits out the exponent, which is y, and that's base 2. So how do I graph this? I don't like to graph these very well. All right. X cannot be 0. Because there's no way to get a 0. Remember, if you take half of a half of a half of half, no way to get 0. And the output's always positive, right? Like even if I sub in negatives or whatever, this output's positive. So X has to be greater than 0. But let's graph this. All right. So the easiest way, I think, is to flip I like to graph 2 to the X and flip it. So if this is at 0, 1, this is going to be at 1, 0, right? The inverse. If this is at 1, 2, this is going to be at what? 2, 1. This guy was at what? 3, 8. So at 8, 3. So 1, 2, 3, 4. Well, 4 is going to go to 2, right? 5, 6, 7, 8 is going to go to 3. And then these guys are going to flip 2, right? So at a half, you're at a -1. So, and you can see, I'm not very good at graphing. It's symmetrical, remember, to y equals x. So remember, y equals x, inverses are symmetrical. So if someone ever asks me to graph a log, I actually find the inverse function and I graph the exponential, and then I just reflect it over, because that I think is way easier. All right, that's just the intro. I will do more in my next video.